Graphs, the representation of probability distribution using a graph as a data structure. So an example of a partially directed graph K. So this is graph is partially directed. Why? Because you can see for some of them from B to E you have an arrowhead. So here you have a arrowhead. Whenever you have an arrowhead, we say it is directed. But from D to E you have no arrow header, which means it is undirected. So an example of partially directed graph, because everywhere there are no arrowheads, so some of them are undirected, some of them are directed, so we say it is partially directed graph. Nodes and edges. A graph is a data structure K consisting of a set of nodes and a set of edges. So your nodes is what? D to E. If you are moving, then D and E are your nodes, and this arrowhead is the edge. A set of nodes is x equal to x1 till xn. Directed edge. A pair of nodes xi, xj can be connected by a directed edge xi to xj or an undirected edge xi to xj. So directed means you have an arrowhead. Undirected, if you can see, there is no arrowhead. Undirected edge. Thus the set of edge E is a set of pairs where each pair is one of xi till xj, xj to xi or xi to xj. So you can either say undirected as edge as going from xi to xj or xj to xi, or you can represent it as xi and there is no direction till xj. So you can go vice versa. Over here you can only move from D to E. You cannot move from E to D. This is wrong. But for undirected, you can move from, suppose if this is the edge given to you, then you can move from xi to xj, and you can also move from xj to xi. So in short, you can move from xi to xj in a undirected manner. For each pair of nodes xi, xj, at most one type of edge exists. Thus, we cannot have both xi to xj and xj to xi, nor can we have xi to xj and xi which is undirected to xj. So we cannot have this xi to xj and xj to xi. You cannot have directed edge like this, because in directed edge from one point only it can move to another point. So from D only it can move to E, from xi only it can move to xj. Vice versa is never true. And if it is a directed edge, then it cannot be undirected, of course. xj to xi is equivalent to xj to xi. These two are equivalent. What does this mean? That you are going from xj edge to xi edge. And xj to xi is equivalent to xi to xj. That means it is undirected. You can move from j to I also. From j to I also you can move. And from I to j also you can move. So for undirected, we say that from D to E, if D and E are connected with the help of an undirected edge, we can say that from D to E you can move, from E to D also you can move. But if they are connected with a directed edge, we say only you can move from D to E. So we use xi bidirectional xj to represent the case where xi and xj are connected via some edge, whether directed in any direction or undirected. So it is directed in any direction or it is undirected. So like this, it is directed in any direction or it is undirected. We can use a bidirectional arrow. Directed graphs. A graph is directed if all the edges are either xi to xj or xj to xi, denoted by G. Undirected graph. A graph is undirected if all the edges are xi to xj. So there is no arrowhead when you are going from xi to xj. That is undirected graph, denoted by H. xi to xj belongs to E. xj is the child of xi in K, and that xi is the parent of xj. So xi is your parent and xj is the child. Xi to xj belongs to E. Xi is a neighbor of xj in K and vice versa. Xi bidirectional xj, x and y are adjacent. PAX, parent of x, CHX, it's the children, and NBX, it's neighbor. Boundary x, the boundary of x is equal to PAX union NBX. Boundary of x is PAX union NBX. Directed graph, x is the parent, and for undirected graph, x is the neighbor. The degree of a node x is the number of edges in which it participates. Its in degree is the number of directed edge y to x. So degree of a node is nothing but the number of edges in which it participates. So suppose D is there, you have a E edge, you have a edge which is F. So degree of D, degree will be 2. For E, degree will be 1. For F also, degree will be 1 because it is only participating with D. E is also only participating with D, but D is participating with both E and F. So degree is 2. Degree of a graph is the maximal degree of a node in the graph. So here if you consider DEF as the graph, then degree of this graph will be 2. Why? Because the maximum degree of a node is the degree of the graph. Maximum degree is of D, that is degree 2. So degree of the graph will be 2. So degree of the node is the number of edges to which it is connecting. And degree of a graph is the maximal degree of a node in a graph. A subgraph over X is complete if every two nodes in X are connected by some edge. The set X complete subgraph is often called a clique. Now an example of a partially directed graph, we have already seen this. Subgraphs. Let k equal to x comma epsilon and let x belongs to x. Now we define the induced subgraph k of x to be a graph x comma epsilon hash, where epsilon dash are all the edges x bidirectional to y belonging to epsilon such that x comma y belongs to x. So basically what is the induced subgraph? Now this is a complete graph. You have this complete graph. So in this complete graph, if I take this much part, then this is your subgraph. CDEI is your subgraph. That means a part of the graph. A part of graph is subgraph. Upward closure. A subset of nodes x belongs to x is upwardly closed in K if for all x belongs to x we have that boundary x is a subset of x. We define the upward closure of x to be minimal upward closure subset y that contains x. We define the upward closure closed subgraph of x denoted x plus k to be induced subgraph of y comma ky. Now what do you mean by this? See if you want, then you have to see that which all are getting connected to C. So you have A, C, D, E, B. This part will be coming. If they have asked you for C, D, I, then C, D, I should come. I is connected to E, it is connected to C. So you have to see the connections. So then you will get this graph. So I is connected to what, C is connected to what, and D is connected to what. Only these things you have to check. So suppose in this they have asked you, let me erase this, CDI they have asked you. So for CDI, C is connected to 1 and 2, D is connected to 1 and 2, I is connected to this and this, so and this also. So we will take which part? This part of the graph. In this your D connections have come, C connections have come, even your I connections have come, and even your D connections have come. So see, this is your graph. You don't need this F, right? So that's why they have not taken the F. Next, walk. A walk is a sequence of vertices and edges of a graph. That is, if we traverse a graph, then we get a walk. Vertex can be repeated, edges can be repeated. Walk can be open or closed. Open walk. So 1, 2, 3, 4, 2, 1, 3. 1, 2, 3, 4, 2, 1, 3 is a walk. Open walk. A walk is said to be open walk if the starting and the ending vertices are different. That is, the origin vertex and the terminal vertex are different. So 1, 2, 3. Then you're going to 4. Then you're going to 5. Then you're going to 3. So you have 1 and 3. That is, the starting and ending vertex are different. Closed walk. A walk is said to be closed walk if the starting and the ending vertex are identical. That is, a walk starts and ends at the same vertex. Then it is said to be a closed walk. In a walk, vertices can be repeated and edges can be repeated. Trail is an open walk in which no edge is repeated. Vertex can be repeated. So trail is where no edge can be repeated. So it is nothing but an open walk where no edge is repeated. So your 1, 3, 8, 6, 3, 2 is a trail. Also 1, 3, 8, 6, 3, 2, 1 will be a closed trail. So in a trail is an open walk in which no edge is repeated, but vertex can be repeated. So this is your thing. You can repeat 1 and 1 because it is a vertex. So vertex can be repeated. Path. It is a trail in which neither vertices nor edges are repeated. That is, if we traverse a graph such that we do not repeat a vertex nor we repeat a edge, as a path is also a trail, thus it is also an open walk. Vertex are not repeated, edges are also not repeated. So in a path, vertices and edges are not repeated. Cycles and loops. Cycle. Traversing a graph such that we do not repeat a vertex nor we repeat a edge, but the starting and ending vertex must be same. That is, we can repeat only the starting and the ending vertex. Only then we get a cycle. So vertices are not repeated, even edges are not repeated. But what is the condition? Starting and ending vertex is same. Vertex is same. Loops and multi-edges. A loop is an edge that connects a vertex to itself. If a graph has more than one edge joining same pair of vertices, then these edges are called as multi-edges. So this is where we are done with the graph.